Hello students, I am Dr. Tanmoy Biswas. I welcome you all in my channel Chemistry, the Mystery of Molecule. Today's question is one MCQ in front of you. So arrange the compounds with respect to their decarboxylation rate while heating in aqueous acid. So these three compounds are provided and four options are in front of you. So I request you student, please pause the video, try by yourself, and whatever answer you get, please write in the comment box along with few words as explanation. Because self-evaluation is essential for improvement, and that's why you should try. I believe you have tried by yourself, so it's my turn to give you the right answer. So student, please read the question carefully. This question is little different, I believe. Actually, what is asked? First of all, decarboxylation, heating aqueous acid. So if you understand these 3 points, I guess you will get. So reaction of these 3 carboxylic acid with H plus and heat. So this is the question. What is the product? Now I believe you can do. I have given the first clue. So if you think that you can do, just pause this video and write in the comment box. Now for you, let me explain this. So reaction of proton, and here decarboxylation will happen, means along with that carbon dioxide. How decarboxylation is possible? Actually, it is possible by one method, that is ipso substitution. So let's see how this happens. So first, proton reacts with this double bond. Actually student, this is a model compound, para-hydroxybenzoic acid, such that you can understand the thing properly. So first protonation, and after this protonation, positive charge builds here. So it could be stabilized with the conjugation of these lone pair of electron, means it could be pushed here, it can come. So in this way this will be delocalized. So there are other canonical form also. I am not focusing, just I want to say one thing, how the plus R effect of oxygen is helpful for these protonation or aromatic electrophilic substitution with proton as electrophile, means this one as electrophile. So this is for protonation. Now in the next step, what you can expect, that the sigma complex actually is deprived of aromaticity, and how this aromaticity could be gained, you can look at here. So there are 2 lone pairs, so it could given here, it will open, it will come back, and these bonds, student, this bond can come here. So in this process, what it will do, it will produce this carbon dioxide, and obviously heating is essential for this, and this CO2 comes out from the reaction medium such that reaction can proceed in the forward direction. So at the end, what we got a H plus or proton substitution at the place of this carboxylic acid. So that's why you can consider this reaction as ipso substitution, which is nothing but a kind of aromatic electrophilic substitution. Fine. So in this way we can get. Now let's come back to this. So we talk about para-hydroxybenzoic acid. Now for ipso substitution is nothing but an aromatic electrophilic substitution, and in order to remove this carboxylic acid, actually, means since it is asked that milder reaction condition, you can say that then benzene ring is more electron rich, is more reactive, and we know this phenol is ortho-para orienting and activating. So if you look at this compound A, so in this case this position is para with this hydroxyl and ortho with this hydroxyl, so it's highly reactive. But if you look at in the second case, student, so this compound, this carboxylic acid is neither ortho or nor para with respect to any one of these 2 hydroxyl groups, so very less. Third, in case of option C, this carboxyl group is para with respect to this hydroxyl, but it is meta with respect to this. So this is para, this is meta, so not possible. And similarly, if you look at here, this is meta, so these 2 are meta. We know that benzene increases its electron density using its plus R effect at the position of both ortho and para. So that's why this position will have the maximum electron density for aromatic electrophilic substitution. So here we can expect that maximum reactivity will be A, second reactivity will be B, because one hydroxyl is para with respect to this carboxylic acid group, and third will be C, because both hydroxyl groups are meta for this carboxylic acid. So the order expected A greater than C greater than B. So A greater than C greater than B. So option B is the right answer. Now if this question appear in your exam, you need to keep, actually first I'll say that you need to read the question very much carefully. First, decarboxylation is asked while heating in aqueous acid. So from this carboxylic acid, carbon dioxide will come out and the reaction will happen under heating condition, and here proton is the reactant because acid is mentioned. So if all these three you can understand that, and second thing you need to understand that first of all, this is actually aromatic electrophilic substitution using proton. So more electron rich substituents will go, and decarboxylation will happen, and in place of this carboxyl group proton will be attached, means this proton H plus. Fine. So if you understand this, which case this position is maximum electron rich, obviously A, because it is first one ortho with respect to one hydroxyl, para with respect to another hydroxyl. So that's possible. So option A will be the maximum active. Now use the strategy of elimination. So A must be maximum. So these C and D gone. Fine. Now between first one, A greater than B greater than C or AC. Now let's come to the least one. See, if you see this B, this is meta, this carboxyl group is in meta with respect to this 2 hydroxyl. So rate is expected to be very low, because in case of C, one is meta, one is para. So obviously second position will be secured by C and third will be B. So this is the answer. So but for this purpose, good knowledge on aromatic electrophilic substitution and ipso substitution is essential. Okay. So in conclusion, what we have learned today, that ipso substitution is a type of aromatic electrophilic substitution, and electron donating group increases the reactivity for this AES reaction, and electron donating group in the ortho-para position activates the aromatic nucleus more. And remember student, that ipso complex could get the aromaticity back either by proton removal or by decarboxylation. But if proton removal happened, then the original reactant will get back. But if CO2 elimination happened, then it will result in another product. And since the CO2 is gas and it comes out from the reaction medium, then it helps the equilibrium to proceed in the forward direction, means the ipso substitution reaction. So this is the end of discussion, but before going to the end, I want to give you student one example of this gallic acid. Gallic acid is available on tea, and these gallic acid can undergo decarboxylation very efficiently. So if you look at using the same concept, you can see this carboxylic group is para with respect to this hydroxyl and meta with respect to 2. So it can also undergo decarboxylation upon heating in acidic medium. So similar thing, and in this way what product we get? We get this 1, 2, 3. So we will get, this is 1, 2, 3 trihydroxybenzene derivative. Okay, so this is another interesting information, please remember. So this is the end of discussion. Thanks for watching. If you really consider my contents unworthy, then please help this channel to grow. So stay happy, stay blessed. See you in my next video.